Okay, good morning. This is Professor David J. De Los Reyes. Okay, it's August 22, 2023. The time is 3:02 a.m. It's 3:02 a.m. here in Los Angeles, California. Okay. My topic for this morning will be college algebra, and this will now be on the so-called application of quadratic equation that involves maxima and minima problems. This is not differential calculus, but since we are tackling the topic quadratic equation, and quadratic equation actually involves the graph of a parabola. For a parabola, there will be the so-called maximum and minimum point. And there are problems, okay, in which the problem is asking for a maximum value. So for tonight, let's proceed. Okay, let's proceed. Okay, Professor David J. De Los Reyes, my long video format discussion for this morning will be college algebra, lesson number 39, and the title of the topic will be quadratic equation, example of a maxima problem. The problem is asking for a maximum value. It's a practical application. So even though we are just still on algebra, okay, we got already a practical application. Because when we reach differential calculus, okay, this problem could also be solved by presenting a differential calculus solution, a more accurate presentation of a solution. Okay, let's proceed. I will try to give you a problem. I will try to read the problem. A long rectangular sheet metal, 24 inches wide, is to be made into a gutter by turning up two sides so they are perpendicular to the sheet metal. How many inches should be turned up to give the gutter its greatest capacity? Oh, sorry for that one. Okay, I'll get this piece of paper over here. So it seems we are given a 24 inches wide sheet of metal, okay? And this metal is to be made into a gutter by turning up the sides. Meaning to say, one side is equivalent to the height of the other side. So the orientation will be something like this, right? So the total length is 24 inches, and by turning up the sides, we let this as x, and this is also as x. So the bottom portion should be the total length minus 2x. And this is a gutter, right? For the gutter to have a maximum area, the maximum capacity, the area should be the largest, the side area, okay? Because if we get the side area multiplied by the length, okay, we will have a greatest volume possible that it could hold water, right? So if the area is maximum, of course the volume will be maximum. So the solution, we will just go to the relation of area in terms of the unknown variable x. Okay, let's proceed. To bring out the figure, I'll repeat it. The total width of the metal is 24 inches, okay? So this is 24 inches going around. So after turning up the sides up, okay, this is x, sorry for that one. The bottom portion should be the total length minus twice x. This is 24 minus 2x. And the problem is only asking what will be the value of x, meaning the height of x to be turned up. okay, for the area to be maximum. Area meaning the greatest capacity, okay? Okay? Greatest capacity, if this portion here is big, of course, we could say that the capacity is the greatest, right? So it seems we are given a rectangular area. For our representation, we will let x to be the side to be turned up from both sides, okay? So if we try to bring out the solution, for a rectangle, area in general is actually the product of length times width, okay? This is from solid mensuration, right? The formula for taking the area of any rectangle, it should be the product of length times width. If we consider this one as the length should be 24 minus 2x. Okay, and the width, it will just be simply x. This is multiplied by x. Because the area of the grain area, the one carrying the water, is actually the product of x times the quantity 24 minus 2x. So area, the carrying capacity of the gutter will be 24 minus 2x times x, expanding this. Area will be 24x minus 2x squared. Rearranging this one, since we are on algebra, we must have to bring out our equation in the so-called standard form. Okay, area will be, we write this one first, so negative 2x squared plus 24x. I place a plus 0 here because I am thinking that our equation is of the form y is equal to ex squared plus bx plus c. Okay, that's the form. And we replace this y here by a. Okay, so still our representation on the right hand side is still x, so we will just replace the y by a, and this now here is similar to this, right? So in here we could conclude that the value of a, the coefficient of x squared is negative 2, okay, and the coefficient of b is actually positive 24, and the value c is equal to 0. We are lucky c is 0, right? Our computation will be a little bit simpler, right? Without the value c equal to, with the value c equal to 0. From the value a equal to negative 2, from our previous discussion, since a is less than, negative 2 is less than 0, right? It is to the left. Negative 2 is less than 0. And according to our lesson the last time around, it should be a parabola that opens downward. Okay? Because a quadratic equation is actually a parabola. It either it opens downward or it opens upward. But since the problem is asking for a maximum greatest, okay, so greatest is synonymous to maximum. And since the value of a is negative 2, it just confirms that this equation here have a maximum value. Okay, and the location of the maximum value is at the so-called vertex of the parabola. And to compute for the coordinates of the vertex, hk, okay, the last time around, the formula for taking the edge of the vertex is actually this formula here, right? X or h equal to, the one I am telling you that it was not presented, our college algebra textbook just give us this one without presenting any proof. But I discussed to you that it was derived from differential calculus. That is, x or h for a parabola that opens downward should be negative b over 2a. Whether upward or downward, it doesn't matter. But for this is a general equation. So if we now try to compute for the value of x, which will give us the maximum area possible, it should be negative b. And the value of b is 24. So negative open quantity positive 24 over 2 times the value A. What is the value of A? Negative 2, right? So negative 2. So a negative over a negative will be positive because there is no such thing as a negative distance, right? So it just confirms that a negative, sorry for that one, a negative over negative will be positive. So a 24 over 4, the unknown value of x is 6 inches. So for the given problem, the side to be turned up is 6 inches and the other side is also 6 inches. So 24 minus 2x is 12 inches. So meaning to say, for the gutter to have a maximum capacity possible, okay, it should be turned up 6 inches on one side and 6 inches on the other side. Okay, they should be perpendicular because the condition in the problem, they should be perpendicular, right? And the bottom portion will be 12 inches. And if we try to check it, according to the problem, the total distance or the total length of the sheet of metal is actually 24 inches. So this is 6 plus 6 plus 12, that's actually 24. So the value of x, which will give us maximum capacity, it should be x equal to 6 inches. And the maximum area possible, just go back to the given equation, put the value of x. The maximum area possible is 72 square inches. The area that will be covered by water will be 72 square inches for the capacity to be maximum. And the graph of the equation is this one. This is A and this is x. So it seems we are found with y equal to a function of x, right? But now we replace the y with a. So the ordinate will be a-axis, area axis, and the abscissa will be the x-axis still. And the graph of the parabola will be, the value of x is 6 inches. 1, 2, 3, 4, 5, 6. This is x equal to 6 here. So this is 6. And since the parabola opens upward, this is the graph of the parabola. And the location of the vertex, which give us the maximum area possible, is actually at the location 6 and 72. So this is 6, and this side here is 72 cubic inches, square inches. So the location of the vertex is at the location 6 and 72, meaning the abscissa is 6, and the volume at this location is actually maximum, and that is 72. So the vertex is at the location 6 and 72. That's the one. That's the parabola. It opens downward, so there is a maximum point, and the location of the maximum point is actually at the so-called vertex, because it refers to the so-called greatest capacity. Am I still on camera? Okay, let's try to check the validity of our answer. For the next discussion, I will be presenting the differential calculation. We check our solution by using differential calculus. Okay, from the algebra solution, we derive already area in terms of the variable x, right? Area is minus 2x squared plus 24x. This is an AC problem under differential calculus. Because to get the maximum area or the value of x, which will give maximum area, we will take the first derivative of this. A is variable, x is variable, taking the differential of both sides. Differential area over differential x equal to the differential of the right hand side, constant in a function negative 2. The differential of x squared will be 2x times 1, power formula, plus the differential of 24x, 24 times 1. We are differentiating with respect to x. And we will set the differential area with respect to x equal to 0 for maximum area. Okay? Because under the study of differential calculus, the differential of y with respect to x is actually slope. And for maximum point location or minimum point location, they should be 0. But we will replace this y here by differential area, by area. So at this maximum point, okay, the slope of the tangent line at the maximum point, that is dA over dx, is equal to 0. So if we will equate dA over dx equal to 0, we could compute for the abscissa of this point here. So equating dA over dx equal to 0, 0 now will be equal to negative 4x, simplifying this one, plus 24, or 4x is equal to 24, x will be equal to 24 over 4, and that is actually 6 inches. So it just confirmed that by using the so-called differential calculus solution, the value of x, which will give the volume maximum, is actually 6 inches. And to compute for the maximum volume, just go back to this. Place the value of x to be equal to 6 inches, and what will come out will be 72 square inches. So meaning to say, this location here, by presenting differential calculus solution, is actually with the coordinates 6 and 72. From the first solution algebra, okay, the coordinates, the vertex represents the maximum point, right? And the location of the vertex is at 6 and 72. And by using differential calculation, we have proven that x is still 6 inches and the area max is still 72 square inches. Okay, that is the so-called differential calculus solution. So I place it here, it is true. Okay, so this is the algebra solution. Okay, by using the location of the vertex, which will give us the maximum point. And for the differential calculation, we are given the equation. We will take the first derivative. We will equate it to 0. Because under differential calculus, for maximum and minimum value, okay, we set the slope to 0. Even if the graph is minimum, right, minimum, dA over dx will still be 0. But for this given problem, it so happens that our graph is actually at maximum. So I'm telling you, whether minimum or maximum under differential calculus, okay, we set the first derivative to 0 to compute for the value of x, which will give us the greatest area. Okay, that's it, guys. So for those of you who are taking up college algebra, this is for you guys. If you want to subscribe to my channel is at youtube.com/@Prof. If you want to share it, please click share. Okay, good morning from Los Angeles, David J. De Los Reyes, Professor David J. De Los Reyes. We have presented an algebra solution and the differential calculation, and they just confirm each other. Okay, good morning from Los Angeles, Professor David J. De Los Reyes.